Okay, we're going to get started here. Let me do something quick. All right, we're going to do a quick run through chapters 11, 12, 13 homeworks. And so let's start off with chapter 11 here. The visible spectrum is a small part of the whole electromagnetic spectrum. Electromagnetic spectrum ranges from gamma radiation down to radio, TV waves. Name several other parts that are included. And so here's the visible. What other parts are there? Well, probably UV is everyday. Everybody knows UV. And X-rays, maybe, UV and X-rays. Yeah. Well, any of these other parts, probably everyday. Microwaves, of course, microwave ovens, radio waves. So all these other parts are very common, but you can't see them. Actually, this is only a very small portion of the entire spectrum, between 390 nanometers and 760 nanometers in wavelength. It's not that big of a part, electromagnetic spectrum. Identify measurable wave properties that are used. Wavelength and frequency. Wavelength and frequency. Also velocity. Velocity is the constant speed of light. Wavelength and frequency differ for different types of electromagnetic radiation, but the velocity is all the same. So radio waves travel exact same speed as gamma rays. We'll just do the ones with the answers. I mean, we could do all of them, but some of them do get problems. What do visible light and radio waves have in common? They move at the same speed, velocity. Which of the following is not quantized? The number of plastic bags in a box, that's quantized, because you're going to have 1 or 2 or 3 bags, but hopefully not 1.1 bags. Then that's probably a defect. Cars passing through a toll plaza, that's going to be quantized. Birds in an apiary, that's going to be quantized. Flow of a river in cubic meters per hour, this is going to be continuous, cubic meters. If we're looking at the flow of the river in molecules per hour, then that would be quantized because you can't have like a half a molecule flow. But if you're looking at cubic meters, then it should be no problem. That should be continuous. That's macroscopic versus, at the particulate level. The macroscopic level, you don't notice that the water in the river is actually quantized because the particles are so small. So it appears continuous. You don't really notice it. This is like a glass of water. When you have a glass of water, you can have any amount. But once you start getting to particulate level, then that glass can contain 1 water molecule, it can contain 2 water molecules, but it can't contain 1.5. So then it becomes quantized. And so this is why the earlier physicists didn't really notice quantization, because it only really happens at the particulate level of any significance. Percentage of salt in a solution, that should be continuous too. You should be able to get, any saltiness up to the max, 100%. 100% would be the maximum. It would be like humidity, You can't put an infinite amount of salt in the solution because of solubility concerns. We'll talk more about solubility in chapter 16. But there are some things that you could dissolve an infinite amount. Those are called miscible. But salts are, salts in the solution are typically have a limit, even things that are highly soluble. But the percentage should be continuous, from 0% salt to 100%, which would be saturated. We call it saturated. What kind of light would atoms emit if the electron energy were not quantized? It would emit a continuum, if the electron energies were not quantized. Electron energies in an atom are quantized in an atom. But if the electrons are free, relatively free, the atoms are a very small aquarium, or it would be like a small aquarium. And the electrons are confined to that small aquarium, they're going to be quantized. But if the electrons are free, that is, if they're in a big piece of tungsten metal, then essentially that's like a big ocean, Or like electrons in the sun, which are free, to move about. then those are continuous. Yeah, all colors of light. So this is called a continuum. What must be done to an atom? Not just visible, but we do have infrared and ultraviolet. The earlier physicists noticed something. They're expecting a lot of ultraviolet light. You keep heating up the electron, you're going to start emitting a lot of ultraviolet light, which is going to cause some trouble. But what the earlier physicists noticed is something called the ultraviolet or the UV catastrophe, in which they didn't get nearly as much ultraviolet as they were expecting. And so that had to do with quantization of energy. What must be done to an atom, or what must happen to an atom before it can emit light? It's got to be excited, either electrically or thermally, collisions. It's got to be excited. And in order to get excited, it absorbs energy. And so you get to an excited energy state, which drops down to a lower energy state. Which atom is more apt to emit light, one in the ground state or one in the excited state? The ground state is already stable. The ground state is defined as the most stable state, so it doesn't want to emit any energy. It's already at the lowest. In an excited state, it's going to emit the energy. In the ground state, it cannot emit light, is what they're saying. There's no place for it to go. Excited states can. Using a sketch of the Bohr model of an atom, explain the source of the observed lines. Yeah, this is going from the orbits. We outlined it. It's going from two observed visible lines. These lines are actually not the visible ones. 2 to 1 is in the ultraviolet. 3 to 2 is the red line. And then 4 to 2, and then 5 to 2. It's going to the second floor. 2 to 1 is a bigger drop, and so that's ultraviolet. So that's all the lines, not just the visible, but the ultraviolet. They had the different series, Balmer series, etc. Identify the major advances that came from the Bohr model. Major advances was it was able to explain the hydrogen line spectrum as a major advance. Also talked about quantization, but the Bohr model didn't really talk about why certain orbits are forbidden. The Bohr model, you just had to accept it, as a postulate. Why are those orbits forbidden? Well, they're forbidden because that's what's observed. But, there wasn't really a fundamental description of why that particular orbit, a little bit farther out or a little bit farther in, is forbidden. And so that left, kind of a question hanging, an obvious question hanging, why couldn't those orbits exist? Well, so they said the Bohr model provided an explanation for atomic line spectra in terms of electron energies. It also introduced the idea of quantized electron energy levels. Unfortunately, Bohr models no more. Compare the relative energies of the principal energy levels within the same atom. Relative energy. Principal energy, n equals 1 to n equals 2 is going to be, n equals 2 is higher in energy, right, etc. Energy is actually, the energy is given by I didn't write this equation down, but the energy is actually given by the Bohr model, and we get the same energy for the hydrogen atom, for the H atom. The energy is minus R sub H over N squared. And so the higher the N, we can figure it out. The smaller the more, minus R sub H. The highest energy, it's weird because the highest energy is if N goes to infinity, this goes to 0. And so the highest energy is actually 0 because that's the reference point. This is arbitrary 0. It's not really 0 energy here. There's energy still, but they're just looking at the energy between the proton and the electron here being separated at an infinite distance. And so the lowest energy is minus R sub H over 1 squared. That's the lowest energy. This is actually minus 2.18 times 10 to the minus 19 joules or so. But we don't need the numbers. Chem 1A, you'll do some calculations. We get this exact same equation from the Schrodinger equation. And so when we solve the Schrodinger equation for the hydrogen atom, this is the equation that comes up. Well, this is the same equation that they got in the Bohr. Well, it's gotta be the case because the quantum mechanics model, it's got to be a fundamental description of it, and it's just the Bohr had the wrong interpretation of it. And Bohr couldn't go beyond the hydrogen atom, of course. How many sublevels are present in each principal energy level? Well, it's the same, N, there are N sublevels. Talk about that. I forgot to go through these earlier. Is equal to N. So N equals 4, there are 4 sublevels. With N equals 4, that is. So how many sublevels are there in an atom with N equals 4? 4. S, P, D, and F. How many orbitals are there in the S sublevel? 1. P sublevel 3, D sublevel 5, F sublevel 7. Those are common. These numbers you should know. You could also figure it out by the quantum number rules. 1, 3, 5, 7. Each P sublevel contains 6 orbitals. That's false. Each P sublevel contains 3 orbitals, but holds a total of 6 electrons. The principal energy level with N equals 6 contains 6 sublevels, although not all 6 are occupied for any element now known. Is this true or false? This is true. N equals 6 has 6 sublevels. So N equals 10 would have 10 sublevels. Talked about that earlier. An orbital may hold 1 electron or 2 electrons, but no other number. Is this statement true or false? That's true. What principle is that? Or it may be empty. That's false. Sorry, it could be empty. May hold 1 electron or 2 electrons, but no other number. I guess 0. I wasn't thinking about 0. So that got me. It was a little bit tricky. It's the Pauli exclusion principle. This is question number 28. What is your opinion of the common picture shown? Okay, this common picture is shown. My opinion is this is wrong. This is a Bohr model. It's wrong. You can read this, talk about it. What is the largest number of electrons that can occupy the 4p orbitals? 6. Right? The 3d, d is at 10, 5s, 14, 7 orbitals, 14, 6, 10, 14. Energies of the principal energy levels of an atom sometimes overlap. Explain how this is possible. Energies of the principal energy levels of an atom sometimes overlap. I don't know what they're talking. For elements other than hydrogen, the energy of each principal energy level spreads over a range related to the sublevels. I don't really get that. All right, skip it. Which of the following statements is true? The quantum mechanical model of the atom includes all the Bohr. No, that's false. Part of the Bohr model, that's true. No part. The part of the Bohr model, its energies are quantized. That's part of the Bohr model. Energy levels appear, in other words, quantized energy levels. What do you conclude about the symbol 2dF? 2d is not possible. That violates quantum. And d would be n equals 2, so the max L is 1. Which would be a P. D would have an L of 2, so it's impossible. Incorrect. What element has the electron configuration? So this is in the third shell, third period, 3s2, 3p4. So we filled the first. what would that be? That would be 6 valence electrons. This would be sulfur. We'd have to, if you have the periodic table, I don't want to bring up the periodic table. We could figure it out based on the periodic table. Or we could figure out based on the number of electrons. The number of electrons for a neutral atom is equal to the number of protons. So it's 2 plus 8 is 10 plus 6 is 16 electrons. What has 16 electrons? Sulfur. 16 electrons. What is the argon core? Argon core is the, helium core is the first shell. Neon core is the second shell. So it's filled the third shell. So it's filled first, second, and third shell. So first shell is filled, 1s2. Second shell is filled, 2s2, 2p6. Third shell is filled, 3s2, 3p6. What is meant by neon? This is the core abbreviation we use. So we don't have to write all the filled shells here. Identify the elements. The 2 ways to identify, just total up the number of electrons. That should be the number of protons of the neutral atom. Or we could just figure it out. You know, this is fourth. Fourth one with 6 valence electrons. Fourth one with 6 valence electrons, if you know the periodic table is selenium. This, you could just look at the periodic table. This is the second shell, second period, with 6 valences, got to be oxygen. 6 valence electrons is oxygen. This one's going to be 2 valence electrons in the third row, which is magnesium. And then this one is helium. This is going to be the second with 5. And so the second row with 5 valence electrons is nitrogen. And this would be the third row with 3 valence electrons. It would be aluminum. And this would be the fourth row with D7. This one I'd probably look at the periodic table. D6 is iron cobalt, but the way I would probably do it is looking at the periodic table. I could just you know, really write them out. You know, potassium, calcium, potassium, calcium, scandium, scandium. Actually, let's see, potassium, calcium, scandium, titanium, vanadium. This comes up manganese. 1, 2, 3, 4, 5, 6. No, sorry. Chromium, manganese, iron, cobalt, nickel. So this is a 4s2 would be calcium, and then this would be 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, cobalt. I'm going to just look at the periodic table. I should have just brought up the periodic table a little faster. Cobalt. I'm doing it from most people. You know, eventually you reach a point where you have to memorize the first 3 rows. You know, the first 3 shells, or first 4 shells. Actually, the first 4 shells is it. So eventually there's a point where you have to memorize the first 4 shells, but you really don't have to memorize beyond that. You work with a lot of transition metals to do that. For Chem 4, you don't have to. You just look at the periodic table. Write the complete ground state configurations. So magnesium, complete, we can't use the Nobel gas for. So magnesium's third. Or actually, what is magnesium? Magnesium is third shell, you know, 2 electrons. You just use the periodic table to do these. Do you guys want me to do any of these, or is it pretty straightforward? Periodic table. You have to memorize 2 exceptions, though. The 2 exceptions you have to memorize in electron configuration are chromium and copper. You know, for chromium, we predict, you know, chromium's here. This is chromium. This is D4. So for chromium, what we predict is if we could use argon, can we use that? No, we can't use the noble gas core. I would like to use the noble gas core argon, but I can't. So I have to fill up the first three shells. 1s2, 2s2, 2p6, 3s2, 3p6. So that would be argon right here. And then we go to 4s2, and then we go to 3d, 4s2, 3d4. But this is one of the exceptions, remember? Half-filled D subshell is more favored. And so what happens is the S gets promoted to the D. So it goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So this is weird here. But that's because we have the half, the half slice cake that I showed earlier. Selenium, we could just use it. All these we could use as periodic table, but this copper and chromium, we have to watch out. Now, copper, on the other hand, I'm going to use the argon abbreviation. And so this is the first three shells, so we're going to go straight to the fourth shell, 4s2, 3d9. Well, this is one electron short of being filled. And so rather than that, copper goes argon, 4s1, 3d10. And so a little bit of energy to promote that S electron, but we get energy in return from having a filled D subshell and a half-filled D subshell. A filled D subshell has an additional stability, and the same thing with half-filled. Half-filled is not going to be as significant as a filled. Selenium, we'll just get off the periodic table. So here, do you see the exception here? It's a 4s1, 3d5. That's an exception. We would predict 4s2, 3d4, but you have to know about half-filled. Selenium, using the periodic table, it's in the fourth period. So we fill up the Ds, and then we add 4 more p electrons, and then we're at selenium. Selenium has 6 valence electrons. This filled D subshell is unreactive. And so the valence electrons are going to be the 4s2 and the 4p4, the outermost electrons here. Sometimes the Ds can participate as valence, even though these are inner, and inner being they're much smaller orbitals. But sometimes those can participate if it's a partially filled D. So for example, chromium, what are the common charges of chromium? The common charges of chromium are actually +2 and +3. So if it's +2 as a common charge of chromium, then we knock out the 4s1, and then we knock out 1 of the Ds. And +3, we knock out 2 of the Ds and the S. And so that is kind of weird. Let's discuss more in Chem 1A and Chem 1B. I don't want to get into it in Chem 4. If it can be done, rewrite the electron configurations for 47 and 49. We're using the core. It's simple enough. Here we filled the first shell and the second shell. And so that would be neon. Then, so we could just do neon 3s2. Here it's the first shell, the second shell, and the third shell. So that would be argon. This would be argon 4s2, 3d8. Same thing here. First, second, and third shell would be argon. 4s1, 3d5. First, second, and third shell. This would be argon. 4s2, 3d10, 4p4. So this is too short of filling the fourth shell. The 3d are in the fourth shell. So we have that there. Move faster. This is silicon. This is actually a single crystal of silicon. They don't want, this is one big crystal of silicon. It's kind of weird looking, but that's how they grow it. Then they can slice wafers out of that. They want single crystals because if you have multiple crystals that are kind of held together, then you have these interfaces between the crystals. Actually, you probably don't even, sometimes the crystals are so small you don't really see them. And so let's look at Sometimes you don't see it. You know, the alloy, it looks like, you know, it's like a single crystal, but when you magnify it at high magnifications, you see each of these is a crystal. And the crystals are just clumped together in a way that it depends on how the crystals are. This is a single crystal here, this bismuth. But oftentimes metals are polycrystalline, and they're held together like this, but a single crystal would be stronger. Makes sense. So we can see here you can see the grains, the metallic. Each grain is a crystal. You can see the grains. Maybe an alloy would be better. I wanted a color one. You can see the different ones here. This is an alloy here. Sometimes alloys are just tiny crystals of other metals embedded in there. Sometimes alloys are actually like defects, like impurities in the original structure. Like this. It's more three-dimensional. It's pretty interesting. You see how we have all these crystals, metal. This is polycrystalline. Single crystal would not be like this. A single crystal would just be one big crystal. Whole thing. This is tiny. You can't even see this with your eye. It looks totally homogeneous with the eye, but under magnification, it looks quite heterogeneous. If you slice this, it looks very homogeneous. Look at it under a microscope. Oh, I don't, okay, this is not this. Vanadium. So we look where vanadium is on the periodic table. And so vanadium is D3. Third one on the D, 3D. And so this would be argon 4s2 3d3. Argon 4s2 3d3. That's just because I have, you know, I can visualize its position because I've seen, you know, it's a repetition. You've seen the, oh, shoot. Yep, okay, I forgot to do that. How did I forget to do the Zoom link? I'm distracted with something else. All right, thanks for letting me know that no wonder. Let's wait a little bit and then pause the recording. Sorry about that. I forgot to post the link on Piazza, and I didn't notice it until just now. Anyway, you can catch the recording, the first 30 minutes. I'm just going through the homework from chapter 11. And so we got up to number 53 here. And so if you want to see the previous problems, just watch the first 30 minutes of this broadcast. That's all we've covered so far today. Just the homework. So let's continue on with this here. Why are valence electrons important? Well, valence electrons are the outermost electrons, and those are going to be the ones that are most reactive. It turns out the core electrons can also be reactive, except they're held much more strongly, and so it requires a tremendous amount of energy to get the core electrons to react, like 10 times more energy than the valence electrons. So the valence electrons is where chemistry happens. And so many of the similar chemical properties of elements in the same column of the periodic table are related to the valence electrons. Yeah, and that's how the periodic table is arranged, based on the valence electrons. They react. Quantum mechanics, basically. The periodic table is based on quantum mechanics here. What are the valence electrons of aluminum? Okay, write both ways that they may be represented. You know, for these types of problems, it's best to have a periodic table, you know. So we can see this position. Valence electrons, it has 3 valence electrons, and so we could represent it as symbols or whatever else, you know. So aluminum here is 3 valence electrons, 1, 2, 3. So I could shrink that down. Oh, all right. What are the ways, write both ways it may be represented? I'm not sure what I'm talking about. Okay. I wouldn't represent it necessarily like this, but that's okay. This is just the outer shell, the third shell, 3s2, 3p1. For the Lewis symbol, we don't generally pair it like that. If we only have 3 valence electrons, then we usually write them separate, like 1, 2, 3, 3 separate electrons, rather than a single in a pair. And I would have shown the valence electrons like this. You know, we have the neon core. The core electrons here are going to be unreactive. And we have the valence electrons 3s2, 3p1. Now, that gets a little bit tricky when we throw in d electrons there. And so below aluminum is gallium. You know. Gallium would also have 3 valence electrons, but it would have the argon core. It's going to have the argon core, but it's going to be 4s2, 3d10, 4p1. Now these 3d10 are unreactive, and so we're going to include those with the core. So sometimes what you'll see is electron configuration for something like gallium is written a little bit differently. This is how we fill it. But sometimes they'll put the 3d10 here next to the argon core, and then they'll write the 4s2, 4p1 like this. And so technically these are the valence here. And these are the core here. Now, when we have a filled D subshell like this, it's very unreactive. Now, if it were partially filled, then there's potential it could react, you know. For example, scandium. Oftentimes people say scandium has 3 valence electrons. Well, technically it has 2, because scandium is, I probably should show you on the periodic table, but if you have your periodic table, just look at it. Scandium is going to be argon, 4s2, 3d1. Now, these 3d1s are considered core electrons because, you know, they're inner shell. You know, the outermost electrons are going to be n equals 4. If you recall, I said that when n equals 4, it's about 16 times bigger, the orbital. So if this n equals 1 is like this, n equals 2 is about 4 times bigger, n equals 3 is about 9 times bigger, n equals 4 is about 16 times bigger. So, this is about, 9 times bigger than n equals 1. This is about 16 times bigger. So these are way out there. And so 3D1, 4s2. So technically it has 2 valence electrons, but this D1 is susceptible to attack. It's not. Filled D is much less susceptible, but this is only filled with 1 electron. This is a very partially filled D subshell. And so even though it only has 2 valence, one of the core electrons can easily react. And so oftentimes, there's only 1 charge for scandium, scandium plus 3. It's scandium plus 3 because we can lose these 3 electrons quite easily. Let's see. Using n for the principal quantum number, write the electron configuration for the valence electrons of group 6A16. Well, group 6 has 6 valence electrons. And so all of them are going to have this kind of electron configuration. We just change the n. We ignore the d's if they're d's because the d's are going to be filled in that case. And so it's going to be ns2, np4. That's going to give us a total of 6. There could be a D, the D's would be n minus 1, the D's. NS2, NP4. They're ignoring the D's, but we saw the D's earlier in there. Let's see. A more complete one. Not one of these sites again. Okay. So let's look at group 6. Here, 6 valence electron. This max, I can blow it up. Here, oxygen is 2s2, 2p4. Sulfur is 3s2, 3p4. But when we get to selenium, selenium is, do you see how they put the 3d10? The 3d10 should split the 4s2. So it should go 4s2, 3d10, 4p4. But to show it in terms of valence versus core, they did it like this. They did argon, 3d10, 4s2, 4p4. So you can see it's the same valence configuration, 4s2, 4p4. Same thing with tellurium. They threw the 4d10s in with the krypton. So these are going to be a lot less reactive. 3s2, 3p4. That's with a filled D. With a filled D subshell, those become, and a filled F, the same thing with filled F as we go down here. The filled F and the filled D subshells are a lot less reactive. However, when we look at iron or cobalt or one of those, +2 and +3 is very common for iron. Well, iron has 2 valence electrons, the 4s2, and then we can pluck off 1 of the D's for +3. But if we're looking at iron +2, we just take off the 4s2, the outermost electrons. And then if a powerful enough oxidizer comes along, you can pluck 1 of the D's. Iron +4 would pluck off 2 of the D's, but that's not likely. The same thing with a lot of these other ones, +2, +3 is very common. So manganese, you know, +2 would be losing the force 2. +3 would be plucking off one of the Ds, which would destroy the half-filled D subshell, but manganese 3 is very common. Chromium is kind of weird because you'd expect +1 because there's only one here. You know, but +2, +3 is very common for chromium. Vanadium is +2, +3, +5. So +2, +3, +5 is, you know, +2 is losing this 4s. +3 is losing one of the Ds. +5 is losing all of the Ds, including 4s. Titanium +4 is very common. That's losing both the S here, followed by both the Ds. So the S are lost first. S are lost first because there's 16 times out there compared to the Ds, because they're 3 and 9 times. The Ds are much closer to the nucleus. Scandium is +2, you'd expect, but +3 is the most common because it's only got one D electron there. It can be easily lost. This is a handy periodic table to have. Here. Just trying to move faster. Identify an atom of the main group element in period 4 that is larger. Okay, so 4th shell, larger than an atom of arsenic. We'll just look at the periodic table. 4th shell, so this one, an atom larger than arsenic. Well, that's easy. Anything to the left should be bigger. Anything to the right should be smaller. So as we go left, it gets bigger. Identify an atom in the main group period element that is larger than the atom of arsenic. Anything to the left of arsenic. Smaller than an atom of arsenic. Anything to the right. When they say main group, they're skipping the transition metals. The main group consists of the S and the P block. The S and P block we call main group, S and P block. The D block here are the transition metals. And so when they're looking at arsenic, that only leaves gallium, germanium, potassium, and calcium as bigger because they're ignoring the transition metals here. When they say smaller, that's selenium, bromine, krypton. Why does atomic size decrease as you go left to right across a row? It decreases because you're adding more protons to the nucleus, and it's the same shell. So you're not adding any shell. So more protons, you're going to have like that tractor beam effect. We call it Z effective in Chem 1A and 1B. As you go left to right across a row in the periodic table, the valence electrons are all in the same shell, or same principal energy level. As the number of protons in an atom increases, the positive charge in the nucleus increases. This pulls the valence electrons closer to the nucleus, so the atom becomes smaller. So even though you're adding, I gave you the example of helium to lithium, Or helium to lithium is probably not the best. Hydrogen to helium. Hydrogen to helium is easy to see. Hydrogen. Helium. Helium is twice the charge. Twice the charge is twice the attraction. And pull the electron closer. But we have 2 electrons. But the electrons try to stay away from each other. And so this electron sees +2, this electron sees +2. Both electrons are going to be pulled in tighter. And so this ends up being bigger, this ends up being smaller. These are the types of things you want to do. When you're going through these types of questions, you want to try to add little annotations or add little notes to help explain it to you, because the best thing to do when you're doing these is to explain it in your own words. If you can explain it in your own words, then you tend to memorize things a lot easier, or tend to remember things a lot easier. So that's what I would do. That's what I did as a student. I go through these and I write little notes to self. So remember, even though an atom of germanium has more than twice the nuclear charge of an atom of silicon, the germanium atom is larger. So this germanium has twice as many protons than aluminum or silicon. Germanium is larger. So, well, if we look at the periodic table, germanium is in the next shell, so we have another shell of electrons. So that's why it's going to be, even though it has more than twice as many protons. This is 14 versus 32, it has more than twice as many protons. It's not smaller because we have another big shell, electrons. And so if you recall, we're in the p orbitals. So this would be a 3p. The difference between a 3p and a 4p, 4p is going to be way bigger orbital. Like, silicon's a 3p. So let's say a 3p is this big. Germanium's a 4p. The orbitals are much bigger, for one. And so it's in the next shell. Another shell. Now it gets a little bit tricky because in one sense they're bigger, in another sense they're smaller. So a 3p orbital in germanium is a lot smaller than a 3p orbital in silicon, but we're not comparing 3p orbitals. If we're comparing 3p orbitals, then yeah, germanium's smaller. But germanium has a 4p, and the 4p on silicon is empty. So germanium has n equals 4 valence electrons, silicon has n equals 3. When comparing atoms in the same group, the number of occupied energy levels is more influential than the nuclear charge and germanium size. What is the general trend in ionizing energies in the same family? In the same family, the family would be the column. Then the higher up, the smaller, and the smaller, the harder. Okay, so chemical family decreases, atomic number increases. Atomic number increases, that means you're getting bigger. So as you're going down, it decreases. As you're going up, it increases. Explain the reason for the general trend in increasing across a period. As you go across, it gets smaller, so the ionization energy should go up. And so, they get smaller because of the positive nuclear charge. Well, it's going to be harder to pull an electron. So this is a good explanation here. This is the reason they get smaller. It's the same reason it's harder to pull an electron from it. What is it about strontium and barium that makes them members of the same chemical family? They have the same valence electrons, two valence electrons, and that's 2. They're all in the same family. One of those family members is very dangerous. The family starts off with beryllium. There's beryllium, magnesium, calcium. Magnesium and calcium, these are important for life. Beryllium is, death, basically. Because what happens with beryllium is very reactive. Beryllium is tiny, very, very, very tiny ion. And what happens is it substitutes for magnesium and calcium, which are much larger, and causes trouble. Magnesium and calcium are important in a lot of biological processes, but if beryllium gets in there, it interferes with things. It's a troublemaker. And unfortunately, a lot of people died from beryllium poisoning. In the South Bay here, because beryllium used to be used in aerospace a lot. To what family? Okay, this is 7, so that's the halogens. 7 valence electrons of halogens. Express NSX, NPY. What electron configures isoelectronic with noble gases? Well, we want the octet. NS2, NP6. That gives us 8. NS2, NP6. 8, the octet, except for helium, excuse me. It was a duet. Identify the chemical family is krypton, in which This is noble gases. Beryllium is the alkaline earth. Call them alkaline earth. Account for the chemical similarities among chlorine, bromine, iodine in terms of electron configuration. They all have the same valence shell electron configuration. They all have 7 valence electrons. They all have 7 valence electrons. What property of atoms of an element determines the element is a metal rather than a non-metal? What property of atoms? The property of atoms. I'm not sure what they're talking about here. Oh, this is a chemical property. What chemical property would be losing electrons? Metals are reducers. They tend to lose electrons in chemical reactions. What are metalloids or semi-metals? So they're at the boundary, between metals and non-metals. So they have properties of both. At the boundary. Let's see if this marks it. You see the boundaries here. It's kind of a zigzag line. Differentiates the metals from the non-metals. It's a gray boundary. Not a black and white boundary. Arrange the following elements in order of increasing metallic character: nitrogen, antimony, arsenic, phosphorus. So we look nitrogen, antimony, phosphorus, and arsenic. Nitrogen versus antimony. Antimony is more metallic. The lower down you go, the more metallic. The further left you go. Arsenic, well, antimony is more. Phosphorus, antimony is more. So antimony is the most, then arsenic, then phosphorus, and nitrogen. Oh, I guess the answer is not there. Give the letters that are in the positions of alkaline earths: Ga, noble gases, Rt. List the letters that correspond to nonmetals, all these. List the elements Q, X, Z in order of increasing atomic size. Okay. Smallest first. QXZ, QXZ, QXZ. Q would be the smallest. X is bigger, and Z is the biggest because that has another shell entirely, another shell of electrons. All right, let's see. Electron energies are quantized in excited states, but non-ground states false. They're quantized in all states. In an atom, electron energy is an atom. A free electron is not quantized. A free electron can go any speed it wants, as long as it's not confined to an atom or a small, pool. And you use a killer whale analogy. So when you look at a killer whale out in the open ocean, that's kind of like unquantized. That's kind of like it's continuous, But when you look at, just one second. Yeah. All right, line spectra of the elements are, a killer whale in a small pool versus a killer whale in the open ocean. Line spectra of the elements are experimental evidence of quantized, yes. Otherwise, we expect continuous. That was the whole thing, They were expecting continuous. Unusual light pattern. Energy is released as an electron passes from ground state to an excited state. No, when we go from ground state to an excited state, energy has to be absorbed because we're going, let's say, from the first floor to the second floor. Energy has to be absorbed. That's false. The energy of an electron may be between two quantized. That's false, but it's in the forbidden zone. The Bohr model explanation of line spectra is still thought to be correct. That's false. That's false. Well, the Bohr model explanation depends on how detailed you want to be. So I can see why they said true. They could say true because what they're saying here is it's jumps between orbitals, not jumps between orbits. So the Bohr model, they're only taking half of it. If you say half of it, yeah, okay, I believe that. But Bohr model's wrong because orbits, Bohr model explained line spectra to be jumps between orbits. That's not correct. If you modify this and say, okay, we're just going to take the jumps part and we're going to lose the orbits part, then you can say it's true. It's jumps between orbitals, not orbits. The quantum mechanical model of the atom describes orbits in which electrons travel around the nucleus. That's false. Orbits is Bohr, and Bohr is wrong thinking. Orbitals are regions in which there is high probability of finding an electron. That's true. All energy sublevels have the same number of orbitals. All energy sublevels, that's false. There's n squared orbitals. The 3p orbitals of an atom are larger than the 2p, but smaller than the 4p. That's true. At a given sublevel, the maximum number of d electrons is 5. No, the maximum number of d electrons is 10 because we've got 5 orbitals. The halogens are found in group 7a. That's true. The dot structure of alkaline earths, that's false. There are 2 valence electrons in alkaline earths, not 1. This would be alkaline metals. Stable ions formed by alkaline earth metals are isoelectronic with noble gas atoms. That's true. Atomic numbers 23 through 45 belong to the transition elements. 23, I don't have the numbers memorized. 23 to 45, that's false. Because 31 through whatever are main group, not transition metals. Oh, 23, and not 23 through 45. I misread this. You have to be careful with multiple choice. Sometimes you can make mistakes by not reading the question carefully. And so I've read it as 2, 45, 23, 2, 45, 23 and 45. That's true. Atomic numbers 52, 35, and 18 are arranged in order of increasing size. 52, 35, 18. 52, okay, is big. That's right, tellurium's big. 35 should be smaller, and 18 should be smaller, yeah. Yeah, that's true. I mean, this is in the 5th shell, 1, 2, 3, 4, 5. 5th shell. This is 4th shell. This is 3rd shell. Sure, they're going to be. Sure. 52, 35, and 18. Oh, increasing atomic size. See, I did it again. I did it as decreasing atomic size. The 5th shell, this should be the biggest. And 18 should be the smallest, but they want it in increasing size. So increasing 18, 35, 52. So you've got to be careful with multiple choice. Atomic numbers 7, 16, 35 are all nonmetals. 7, 16, 35. 7, nitrogen, 16, sulfur, 35, bromine. Those are all nonmetals. That's true. Figure 11-6 shows the spectra of hydrogen and neon. Hydrogen has 4 lines, one of which is sometimes difficult to see. Yet we say there are more lines in the hydrogen spectrum. Why do you not see them? Because they're in the UV and IR. They're invisible. Infrared and ultraviolet. You can't see those. But they're there. You can use detectors to see them. What is meant by the statement that something behaves like a wave? It has wave properties, I guess. Something that behaves like a wave has properties normally associated with waves. One of the, let's see, write the electron configurations that you use for barium and technetium. Nuclear medicine technologist injects technetium into a patient with a shielded syringe. Technetium is the element with the lowest atomic number that has only radioactive isotopes. So technetium is radioactive. Let's take a look at that. What is technetium? Radion's radioactive. Francium's radioactive. Radon is radioactive. Astatine is radioactive. Polonium's radioactive. Bismuth has radioactive isotopes. Lead is not. Bismuth is okay. Well, let's start getting polonium, becomes radioactive. Now technetium is over here. Tungsten. By tungsten. Here's technetium. It's all radioactive too. So it's below manganese, so it's in the same family as manganese. The electron conversion from barium and technetium. So if we do technetium, then we filled up the fourth shell, which is krypton. So we can use krypton as the noble gas core radiation. And then we're at 6. Now, this is tricky now here because we go 6s, 38, 37, 6s1, 6s2, 39. Okay, this is 3D, this is 4D. So 39 goes 4D1. And so our krypton, is it 5s? Sorry, 5s2, 41. And then we go to 40. 42, niobium, 44, molybdenum, 45, technetium, 45. Molybdenum is also an exception. Do you see it's 5s1? I know this is hard to see. I can blow it up more. I can do this one. But technetium is krypton 5s2, 45. Now this is written the other way. Which is acceptable. You know, we could either do it in numerical order or the order it fills. So normally we would have done it the order it fills. The order it fills, it would be krypton. You know, the order it fills is by the periodic table. 5s1, 5s2, 5s2, then 4d, 41, 42, 43, 44, 45, 45. This is not an exception because it's already got half fill. But they rearrange it like this to show reactivity. In terms of reactivity, the most reactive electrons are the 5s2. And so they're going to put these ones. These are less reactive because they're much closer to the nucleus. These ones are more reactive because they're further out from the nucleus. And so this isn't the order that we do. We don't jump to the 40s first and fill those. Well, when an oxidizer comes along, if you're an oxidizer, you come along, you're going to take the outermost electrons. So these electrons are lost first. These aren't. And if we left it like this, it looks like an oxidizer is going to attack the 4D first. The oxidizer doesn't attack the 4D first because the 4D are much smaller orbitals, they're close to the nucleus. They're going to attack the 5s first. And so this is why it's often written like this and not like this. This is how you'd fill it off the periodic table. It's because of reactivity. We're going to knock out the highest end electrons first by an oxidizer coming in. And so +2 should be a common oxidation state for technetium because +2 corresponds to losing these two. If we lose these two to an oxidizer, that's +2. Then maybe we could lose 1 or 2 d electrons. In this case, only 1 because +3 is getting to the max. For a free ion, it doesn't really go much higher than +3 because +3, you know, if you try to form a +4 free ion, it becomes difficult. You know, obviously we can get +4 oxidation states, but it has to be stabilized by something like oxygen or something else. You know, it just doesn't stand alone. So stand alone, the highest ions we typically see are +3, like aluminum. Aluminum is a standalone. We don't need other things there. It's aluminum +3. And we need technetium. So maybe we could lose another d electron. You know, so if we lose 1, it goes to d4. If we lose 2, it goes to d3. Okay. Barium was the other, you know, and so barium is in what shell? 1, 2, 3, 4, 5. Barium's in the 6th shell. And so what would that be? Xenon? So we're not looking at We're looking at the next shell, which would be xenon was 54. So xenon, and then 55 is cesium. So that would be 6s1. Barium would be 6s2. So xenon 6s2. Yeah. So barium, xenon 6s2, technetium's krypton. And they write it the way we would write it, 5s245. But on that chart, they swap these because the 5s are going to be lost first, or attacked first in a chemical reaction. Compare the ionization energies of aluminum and chlorine. Why are these values as they are? The ionization energy for aluminum and chlorine, let's take a look at the periodic table. Which one would you expect? The smaller one should have the higher ionization energy. Chlorine should have the higher ionization. Aluminum is a lot bigger. Not only that, chlorine really doesn't want to lose electron. Chlorine wants to gain electron. Aluminum is probably more beneficial to lose to get to neon. Going from 13 to 10 is easier than going from 13 to 18. For chlorine going from 17 to 18 is better than going from 17 to 10. Let's see how they explain it. Aluminum ions have a lower nuclear charge, fewer protons in the nucleus than chlorine atoms. It is therefore easier to remove a 3p electron from an aluminum atom than from a chlorine atom. So the ionization energy of aluminum is lower. This is a good explanation. Except if I use this explanation, I'd have to introduce shielding in Z effective, which I didn't want to do because this is not correct entirely, because when you go down different shells, then things change, you know. You can't use this argument for everything. If you use this argument for everything, it fails. And so if you use this argument for aluminum versus gallium, well, gallium has more protons, so therefore using that argument, gallium should have a higher ionization energy, but that's false. Gallium actually has a lower ionization energy than aluminum, even though it has more than twice as many protons, you know, a lot more than twice as many protons. And so that's why I didn't use that argument, but their argument's correct as long as you qualify certain things. One of the successes of the Bohr model of the atom was its explanation of the lines in atomic spectra. Yeah, that's one of the successes, but it had a huge failure. Don't overlook the huge failure of the Bohr model, which was couldn't explain anything beyond hydrogen or one electron species. Does the quantum mechanical model also have a satisfactory explanation? Yes, of course, quantum mechanical has a better than satisfactory explanation. It says they're essentially the same. They aren't. You know, Bohr explained it in terms of jumping between orbits. Quantum mechanics explains it as electron jumping between orbitals, not orbits. So to me, they aren't the same. Although the quantum model of the atom makes predictions for atoms of all elements, most of the quantitative confirmation of these predictions is limited to substances. Okay. Of H, He+, H2+. From your knowledge of electron configurations and limited information about chemical formulas given in this chapter, can you identify the single features of all three that make these relatively easy to investigate? Well, the quantum mechanical model involves a Schrodinger equation. The Schrodinger equation can be solved exactly for one electron species. Anything with one electron, we can do the mathematics of the Schrodinger equation exact. So hydrogen has one electron, helium has one electron, H2+ has one electron. All these are one electron species. They can have different numbers of protons and maybe different numbers of neutrons, but the number of electrons is the same. And so that makes them easy to calculate using the Schrodinger equation, but you know, use the computer nowadays to do that. Species with two or more electrons have much more complex mathematics because of how the electrons interact with one another. That's why there's so many lines. When you look at, like, say, mercury, you see so many lines there. It's quite complex. Well, sodium has only 2 lines, you know, but when you look at the lines in the non-visible portion, they're quite a lot. What do you suppose are the electron configurations and the formula for the monatomic ion formed by scandium? Scandium is special, you know. I already talked about scandium. earlier, it's +3. So it's argon, 4s2, 3d1. But we write it backwards. When we're looking at forming ions, we always write it backwards. I mean, not backwards, but in numerical order, 3d1s. We're going in order of progressively bigger orbitals. The 4s orbitals are going to be the outermost here. And so if you're an oxidizer, you attack these first, the 4s, so those get lost. But, you know, if you're still hungry, you can also take this lone d electron. If this were filled, D10, it would be a different story, but it's just a lone d electron, so it's +3. And so the electron configuration for scandium is argon. It's noble gas core. That would be scandium 3+. Argon, so filled the first shell, second shell, third shell. Carbon does not form a stable monatomic ion, so just a reason for this. The stable monatomic ion is going to have too high of a charge. You know, well, I guess +2, but +2 is not all the way there. You know, the charge is too high. +4 and -4 is too high of a charge, and so you know, about +3 is the max. To lose like +4 or -4 is too much. To lose, too much to hold on to gain. Consider the block of elements in periods 2 to 6 in groups 5 and 7. In group 7 are the halogens, group 7A, 17, a distinct chemical family in which the different elements share many properties. Elements in group 6 or 16 have enough similarity to be considered a family. They're called the chalcogens. So the oxygen family is the chalcogens. The nitrogen family also has a name. You know, we have the nitrogen is called the pnictogens. The oxygen family is the chalcogens, and the fluorine family is the halogens. Most people only memorize the halogens, and they don't bother with chalcogens or pnictogens. But, you know, there's a lot of rich chalcogenide chemistry. I used to do a lot of chalcogenide chemistry. And then lots of people who do pnictogen chemistry. Why do you suppose family similarities break down in group 5A, 15? What do they mean by breakdown in group 5? 5 is the phosphorus family. Or nitrogen family. I don't see it breaking down. Nitrogen, phosphorus, arsenic, antimony. These are all similar chemical properties. I don't know what they're talking about. The smaller atoms in group 5 tend to complete their octets by gaining or sharing electrons, which is characteristic of nonmetals. Larger atoms tend to lose. This is not really correct. Nitrogen can gain or lose. That's why nitrogen chemistry is very rich. The same thing with arsenic, antimony. Bismuth is more metallic. Bismuth is starting to look like a real metal. In fact, bismuth crystals are very beautiful. Bismuth metal crystals. Let me show you. These are bismuth crystals here. They're really bizarre. They're like science fiction. These are natural crystals. You just grow them. So bismuth is much more metallic. You know, it's the most metallic of those. The metals are going to want to tend to lose electrons rather than gain electrons. You know, but the same thing happens. You know, it's just the dividing line here. The dividing line, you know, goes like this between metals and semi-metals. So the oxygen family, polonium is considered a metal, you know, polonium, although it's radioactive. Acetine is considered a metal or semi-metal, you know, it depends on how you do that. Antimony is considered a metal. Arsenic is considered a non-metal, but you know, these are all metalloids, this region here. And so I guess that's what they mean, but that happens with all the families. All the families, it becomes more metallic as you go down, so it's easier to lose. It's easier to lose electrons on big atoms. And so I don't really like this question. Xenon was the first noble gas. Let's see. Did I? Okay. I guess I missed the break. We did just that short 5-minute break. Break time. Yeah. Sorry, I missed that break. I wasn't paying attention to the chat. Let's take a break now. It's 12:50. So we'll take a 15-minute break. Pause there. All right, we'll get started again. There is a difference between, like, say, free ion, which would be a monatomic ion, versus, it has to do with the bonding. So, for example, if we look at silicon carbide, in this case, it looks like we have a silicon 4+ and a carbon 4-. But it turns out that if this were 100% ionic, that's what it would look like. But the reality is, it's more covalent. Silicon's a semi-metal. If we look at delta EN is not as big. So this is actually a polar covalent bond. Since it's a polar covalent bond, it helps stabilize this. And so the bonding is not 100% ionic. There's some sharing of the electron cloud here. And so the charge doesn't go that high. And so, but the oxidation states, we would do the same thing. This would be a +4 oxidation state. This would be a -4 oxidation state. The oxidation state is always assuming 100% ionic. And so if it's like not 100% ionic, if it's more polar covalent or more covalent, in other words, then we don't see these high charges. But nonetheless, we still count it. When we're doing oxidation states, we still assume that it's 100% ionic. Why? Because it gives us a good way of comparing different compounds. And for some compounds, it's more accurate. For sodium chloride, it's very accurate because, sodium ions are +1, chloride ions -1. But for something like silicon carbide, we expect much more covalent interaction. So the actual charges aren't going to get quite this high. But the oxidation states are still the same. And so we have to watch out, for these things. And so, for example, we don't see a chlorine plus ion because that would be terribly unstable, but we do see chlorine plus when it's combined with oxygen. This would be hypochlorite, in which oxygen is -2, chlorine would be +1. Now, this is not ionic. This doesn't include, this isn't a chlorine plus ion with an oxide ion. These are oxidation states, and oxidation states tell us about the redox chemistry, how they're going to behave. This whole thing is the ion. It's a polyatomic ion. But doing the oxidation states is extremely useful for comparing redox properties. So that's why we do it, even though the assumption is not always accurate, that the bonding is 100% ionic. 107, xenon was the first noble gas to be chemically combined with another element. So they couldn't get the noble gases to react. And then finally, they have to use a very powerful oxidizer to strip electrons off xenon. Xenon is present in nearly all of the small number of noble gas compounds known today. Note the ionization energy trend. Xenon is the biggest one out of helium, neon, argon. What do these facts suggest? Helium does nothing because helium is too small. Xenon tetrafluoride is here. These aren't stable, these decompose. Xenon has the lowest ionization energy. It doesn't have low, it still has high ionization energy. It's still very hard to ionize it. But it's the lowest of the noble gases and therefore the most reactive of the noble gases. Iron forms two monatomic ions, iron 3 and iron 2. From which sublevels do you expect electrons to be lost in forming these ions? Hint, it is possible for electrons rather than those in the S and P sublevels to be involved in forming ions. Well, if we look at iron itself, just the electron configuration for iron, we could look at the periodic table for that as well. This is how We start off with argon, so argon's 18. And then we go 4s1, 4s2, 3d1, 3d2, 3d3, 3d4, 3d5, 3d6. And so iron, just write it here since the ad's coming here right now. Iron metal itself would be argon, 4s2, 3d6. Now, this is how it fills, but in terms of reactivity, if an oxidizer comes along, what's the oxidizer going to have an easier time with? Is the oxidizer going to have an easier time plucking a D or plucking an S? On the one hand, you think a D because it's higher energy, but you know, D3, N equals 3 orbitals are a lot smaller than N equals 4 orbitals. So N equals 4 orbitals are a lot bigger. So there's a higher probability that this electron is going to be further from the nucleus. And so it's going to take the outermost electrons. Well, the outermost electrons are these, regardless of it being a little lower in energy. And so again, we could write argon 3d6, 4s2. So iron 2 plus is we lose 2 electrons. If we lose 2 electrons, then we end up with argon 3d6. We lost those 4s2 electrons. So this is iron. This would be iron 2 plus. And so the 4s2, we lost those 2 valence electrons. Now we're going to attack a core electron. Well, maybe we can get 1 or 2. We can't get 2 because we go iron plus 4. Iron plus 4 is going to be inherently unstable because of its high charge. For monatomic, we'd have to stabilize it in a polyatomic situation. And so maybe it loses 1 more. Okay, if it loses 1 more, then that's going to have to take it out with D. And so we end up with argon 3d5. Well, 3d5 is a half filled, so that's good. And then also this very high charge. You know, if we lose 1 more and go to 3d4 and iron plus 4, then you know the high charge needs to be stabilized some way. Iron loses 2 electrons from a 4s orbital to form iron 2 plus, and a third from a 3d orbital to form iron 3 plus. This is an example of a D electron contributing to chemical properties. Now, if it was filled like D10, forget it. You know, D10 is not. D10, I shouldn't say forget it. D10 is much less likely to react. Figure 1131 indicates a general increase in first ionization energy from left to right across the row of parity. However, there are 2 sharp breaks in periods 2 and 3. Suggests why ionization energy should increase as the atomic number increases within a period. Well, as atomic number increases, the number of proton increases and the atoms get smaller in the same shell. So that they talked about earlier. Ionization because increasing nuclear charge and the same principle, the same shell, means that the electrons are going to be held tighter and the atoms are going to be smaller. Can you correlate the features of the configurations and locations of the breaks? We talked about the breaks already. I don't know if anybody remembers. Does anybody remember the breaks? I went through those rapidly. There are 2 breaks here. And beryllium to boron. Beryllium, we're removing an S. Boron, we're removing a P. So it's a little easier to remove a P electron than an S electron. So that's show the split. Carbon's a P, nitrogen's a P, oxygen's a P. But the difference between nitrogen and oxygen is nitrogen is an unpaired P, whereas oxygen is a paired P, because nitrogen is going to have 3 unpaired electrons in the 3 P orbitals, whereas oxygen is going to have 1 P orbital paired and the other 2 singles. And so it's easier to remove a paired electron than an unpaired electron. We talked about it. I think I drew it out earlier. Oxygen is going to have this paired, whereas nitrogen's not. Nitrogen's all unpaired. This. So that would be nitrogen. This would be oxygen. And beryllium versus boron, we're moving an S from beryllium, but we're removing a P. P is a little higher in energy. And not as penetrating. Those are the two blips. That's more Chem 1A. I'm not going to expect you to know about the two blips, but in Chem 1A, they're going to expect you to know about the two blips there. Your session has expired. Let's see if it knocks me out of there. All right, that's the homework for Chapter 11. Let's take a look at the homework for Chapter 12. Any questions from Chapter 11? The homework from Chapter 12, write the electron configuration for the ions of the third period elements that form monatomic ions that are less electronic with noble gas. Let's identify the noble gas having. So third shell, you're either going to fill the shell. So if you fill the shell, then you're at argon, or you're going to remove the shell. If you remove the shell, then you're at neon. So it's either going to be neon, which is filled second shell, or argon, which is filled third shell. And so it's going to be neon or argon. Argon emits a violet color when in an activated gas discharge tube. Identified by symbol two positively charged monatomic ions that are isoelectronic with argon. Now this is the color of argon. It's violet. In an argon lamp. This is argon lamp. They're lines in the argon lamp as well. Two isoelectronic. You can just look at the periodic table and see. So argon chloride would be isoelectron, chlorine dichloride, 18 electrons. Or losing potassium ions, we lose one, we go from 19 to 18. So potassium ions and chloride ions are isoelectronic with argon. Potassium ions, losing, sorry, it said losing, positively charged. Potassium ions, calcium ions, etc. Write the symbols of two ions that are isoelectronic with barium ion. Two ions are isoelectronic with barium ion. So barium ion is Ba2 plus. Now we go to Ba2 plus 56. So that brings us to 54. Which would be xenon. So iodide would be 54 electrons, I minus. Telluride would be 54 electrons, T 2 minus. Cesium ion would be 54 electrons. Considering, okay, let's skip that one. Aluminum oxide is an ionic compound. Sketch the transfer of electrons from aluminum atoms to oxygen atoms that accounts for the chemical formula of the compound Al2O3. I showed this as a figure, but you should be able to sketch this. You know, aluminum. It's 3 valence electrons. We should be able to draw the Lewis symbols for this. We'll need 2 aluminums, 3 oxygens. Oxygen is 6 valence electrons. Well, oxygen wants 2 electrons, each one. And so we had come up with a figure like that, and we can draw the Lewis structure. Remember the Lewis structure for aluminum oxide. Let's see what they did. This is a figure from the PowerPoint, the one. Because I draw at least one formula unit, and this one I redrew it. I didn't like it. I do it because even with cations, when you do Lewis symbols or Lewis structures, we put square brackets. And so we did one formula. I already did one formula unit for this. So we're going to have oxide, which is an octet. We're going to have aluminum, which has no valence electrons. And then we're going to have oxide. It's going to have an octet. And then aluminum. And then an oxide. So I don't like this answer. I want to see at least one formula unit, and then you can extend the formula unit in 3 dimensions to get the crystal. That's the lattice, crystal lattice. Now this is a picture from the book, or a figure from the book. When potassium and chlorine react and form an ionic compound, why is there only one chlorine atom for each potassium atom instead of two? Because chlorine wants to gain one, potassium wants to lose one. So 1 to 1. Potassium loses 1, chlorine gains 1. 1 to 1. What is the meaning of orbital overlap in the formation of a covalent bond? I didn't talk about this, I guess. I forgot to talk about this. There are different ways of visualizing covalent bond forming, and it's by sharing the electrons. So one way is just by the Lewis structures here. So let's look at hydrogen. Hydrogen wants 1. This hydrogen wants 1. And so they're going to have a tug of war, and they're going to end up sharing that. So this is one way of showing that sharing. Another way of showing that sharing is hydrogen has 1. And so it has 1 electron in this 1s orbital. And another hydrogen has an electron in the 1s orbital. And so what happens here is this. The two atoms end up overlapping their 1s orbitals, like this. And so we end up sharing the electrons here mechanically. Now, the bond is created by looking at the probability cloud and the density. And so when we look at the dots, this is like the bird, the bird flying out from the nest. When we overlap it, then we get twice as many dots in this region here. So we're going to have more dots where the overlap occurs than up here. Well, that means there's a higher probability of the electrons being between the two positive charges. This is what holds the molecule together, is the electrical attraction between the nuclei and this negative charge density, enhanced negative charge density from the 1s orbital overlap. And so this is called, we have names for this. In Chem 1A, although the book didn't get into this, this is called a 1s sigma bond. Sigma is the symbol. This is a sigma bond. And it's formed by overlapping two 1s orbitals like this. That's how we're going to share. This is this is the light version of quantum mechanics. There are actually two versions of quantum mechanics that are used to describe covalent bonds like this. One is called valence bond theory. Valence bond theory is a little bit easier, but not nearly as powerful. And so valence bond describes a bond as overlapping atomic orbitals like that. The more powerful of the two is the full quantum mechanical treatment called molecular orbital theory. So the orbitals that I was showing in Spartan, those orbitals were molecular orbitals, not atomic orbitals. That's the full quantum mechanical version of it. So let's go back to, this is ammonium here. Let's get rid of the surface. Let's look at the orbitals. Because Spartan is going to do the full quantum mechanical version, so it's going to look at the molecular orbitals. Well, these are the molecular orbitals. These have designations too. But we can simplify things by looking at atomic orbitals, but it gets a little bit more complicated because we don't talk about hybridization. We need to talk about hybrid atomic orbitals. It didn't. It might be easier to see these as transparent. I guess I can't do that. These are what we call molecular orbitals. For hydrogen, generating molecular orbitals isn't too difficult, And in fact, the molecular orbital for hydrogen, if we look at the molecular orbital for hydrogen, it looks very similar to this You know, this is 1s orbital overlap, so it forms kind of this oval type deal here. If we just build hydrogen, hydrogen should be quick, I think. So I'm just pulling it out of the database here. If we look at the molecular orbitals for hydrogen, it kind of looks similar to this we have here. It's slow. No. So sometimes valence bond theory, this simple one, is adequate. I think I have to submit this for calculation, otherwise it doesn't work. Let's see how fast this calculation takes. Hydrogen should be pretty quick, hopefully. Yeah, no, it's pretty quick. Let's take a look. All right, now we can see the orbitals. So do you see this? Let's see if we can look at that transparent. It kind of looks like this, you know. Here's 1s orbital, but this is not, you know, this is actually a molecular orbital. This is what we call an anti-bonding orbital. Anti-bonding orbital, the electron cloud, you see the electron cloud is over here, and not in between the nuclei. So this does not promote bonding. Whereas this is called the bonding molecular orbital because the electron cloud is, you know, the nucleus is here and here, so the electron cloud is inside. In the internuclear region, we call it. So this anti-bonding. See, this is bonding. This would be also bonding. These are molecular orbitals. Orbital overlap refers to the covalent bond formed when the atomic orbitals of individual atoms extend over one another so that the two nuclei in the bond share electrons. Sketch the formation of two covalent bonds by an atom of sulfur and making a molecule of hydrogen sulfide. It's similar to what we did here, except for aluminum oxide, you know, it's winner take all. Here it's going to share. There's going to be more of a tug of war when we look at delta En. That's great. So here we're going to share to form two covalent bonds. This third one I don't like. This is what organic chemists do. Organic chemists ignore the lone pairs, but we don't. And so I don't say or. I don't even bother. I mean, it's not hard to put in the lone pairs there. So it's this one. Don't get into this habit. This is a bad habit to start. Not putting in the lone pairs there. The people who don't need to put it in the lone pairs can visualize it. When they see it, they already see two lone pairs there. It's like the periodic, you know, I can see, even if I don't look at the periodic table, I can see the periodic table in front of me because I've seen it so many times. You know, not the whole periodic table, just the first three rows. Then, even then, I have to fiddle around sometimes because sometimes I forget. Circle about the same thing here. If you can see it without writing it, then it's okay. Go ahead and do that. But if you can't see lone pairs here, then forget it. Don't do that. Circle the lone electron pairs in the Lewis diagram for hydrogen chloride. Well, here, 1, 2, 3, three of them. Just circle around these double dots. Those are lone pairs. This is what we call a bonding pair. This is hydrogen chloride. It's the gaseous form. Cl. Okay. Show how atoms achieve the stability of noble gas atoms in forming covalent bonds. Well, by sharing, they can get an octet. So by sharing, they can get an octet. That's how we counted the electrons in Lewis structures. Remember, we circled them, double counted. Compare the electron cloud formed by the bonding electron pair in a polar bond with that in the non-polar bond. It's going to be asymmetric. It's going to be skewed. There's probably better visuals for this book. There's some different visuals for this. Electron cloud, electron map. Here we can see it, the skewing of the electron cloud. You can also see it in Spartan. Go back to Spartan. So this is our hydrogen. Let's get rid of the orbitals here. Let's look at the electrostatic potential map. It should be green in this case. It should be pretty neutral. It's pretty green, pretty neutral throughout. That's H2. But what if we did HCl? If we do HCl, chlorine, HCl here, I'm going to see if I can just replace that without having to do calculations. Then I'm going to know the electrostatic potential map. Add this. Here we can see that there's starting to be a lot more polarization here. This is becoming much more blue. Blue is positive. This should be becoming more red, except I need to readjust the scale in my electrostatic potential now. Close that. I guess I can adjust the scale. That's odd. I guess I can't do it. That's odd. Refer to 1215 and list the following bonds in order of decreasing polarity. So 1215 is probably the electronegativities, Pauline's electronegativities. This is this chart here. And so we just say, well, carbon-carbon is going to be 0. So we just calculate our delta ENs from there. The biggest would be sulfur. Actually, we don't need to consult the chart. We just get the sulfur, oxygen, nitrogen, chlorine kind of thing. Sometimes we could get it without looking at electronegativities. The highest is fluorine. Positive pole, if any. So germanium, selenium. Selenium's to the right, so germanium would be positive. Bromine versus selenium. Bromine's to the right. Selenium should be positive in this case. Bromine and germanium. Germanium should be positive. Oh, that wasn't the blue. For each, so that's it. Let me do that. Oh, question 21. I was on the wrong question. Identify the trends in electronegativities. Fluorine's the highest, cesium, francium the lowest. That's a trend. Atoms with double bonds and triple bonds can conform to the octet rule. Could an atom with a quadruple bond obey the rule? Yeah, an atom with a quadruple bond could, if that was the only thing that was there. And so let's say if I had something like this, a quadruple bond, then this could obey the octet. There would be 8 electrons on that silicon and 8 electrons on this silicon here. And that would be okay. So quadruple bonds, technically, yeah. In fact, quadruple bonds aren't common. But there are some quadruple bonds out there. One of them has been recently revealed. This is 2012. Boron makes a quadruple bond with rhodium. This is just recent, January 28, 2020. Check that out. I think I remember this when this came out. Yeah. It's showing the orbitals here. These are molecular orbitals. You see these molecular orbitals. So the 2 sigma and the 2 pi. Sigma has a code and pi has another code. It depends on where the nuclei are and where the lobes are. Determine sigma and pi bonds. Now that's interesting. Quadruple bond there. Chemical and Engineering News is another good source. This is a paid site. You have to be a member to access these articles, except for coronavirus articles. Everything coronavirus related is free right now from Chemical and Engineering News. And so where is it? Let's go to the home page. And so here. And so all these are free articles here. Actually, most of these are free. It's if you want to search. So let's see. COVID-19 is probably more deadly to men than women, but scientists still aren't sure why. There have been some hypotheses regarding why. I've seen some of those hypotheses of why men are more at risk. But it's interesting. Men, of course, smoke more than women, but the other thing is, the common things that people would expect, like lung disease or asthma, asthma, that's where this whole idea of steroids came from, because a lot of people who have asthma are inhaling steroids. And it turns out that there aren't the COVID-19 patients with asthma is lower than population, which means, they have a greater resistance to COVID-19 than a worse resistance, whereas people were expecting the opposite, And so there are hypotheses for that. But I read some of the hypotheses for this, especially in regards to like Italy and other places there. But those are all hypotheses. Hypotheses are tentative, remember, tentative. Theories are widely accepted. However, people get those two terms mixed up all the time. First U.S. phase 3 trial of COVID-19 vaccine begins. Enroll 30,000 people. Why isn't it in the collections? Oh, here it is. So everything we know about COVID-19 coronavirus is all free. And there's some stuff that you would actually have to pay, quite a bit of money to access if they didn't give it for free. One of the things that you would have to pay quite a bit of money are some of the journal article reprints. And so let's find some of those. And some of those, you might be interested in if you want to see some scientific publications. Let's take a look. Oh, I didn't know this. U.S. pre-orders COVID-19 vaccine and antibody therapy. This was interesting, the accuracy. This is another thing that people are talking about. Does it really have to be high accuracy? They just want to get a test that targets infectious people. And they're talking it's too accurate. You know, the PCR test may be too accurate because it's catching fragments, and those fragments are people who are testing positive, but they aren't really infectious. That is, they can't spread the virus because they just have fragments of the virus, not live forms of the virus. Homemade masks. The articles are way back. Hydroxychloroquine. There's a lot of news about hydroxychloroquine. But, you know, the thing is, it's good to have a healthy debate about hydroxychloroquine. You know, you have the people who support it and the people who are against it, but, you know, let them fight it out, you know. Don't silence one side. This is, you know, of the debate. It's good to have a healthy scientific debate about these things. Dexamethasone, you know, remdesivir. Isn't the cure, you know. Just 1 second. Okay, I got to, let's see, today's Wednesday. Yeah, okay, can we, I have to take a break here, a little bit early break. I have to take care of something, so can we take a break here for 15 minutes? And we'll start again after that. Let me show you one other thing. Multiple clinical trials test whether NO gas can treat and prevent COVID-19. Something interesting. Rethinking the role of blood pressure drugs. Oh, this is CND News, and so if you keep going down here, they provided open access to all COVID-19 related journal articles. And so I ended up copying all of them. I mean, downloading all of them.